Okay. So this is different. But I mean, if you don't understand proof, then it's fine. Yeah. Okay, so the rest, so the final small topic is for the polar and singular gravity composition. Uh, this is important. So there are two. So in your linear algebra course, you heard about this diagonalization, but in fact, that most there are a lot of matrices. Not all matrices you can do the diagonalization. So in linear algebra, then usually there are various ways to do for various decomposition for general matrices. So one is called the Jordan form, which is very complicated and use some algebra. So unfortunately, that one is complicated and seldom used outside the academia. So the most important one used in the machine learning or like computer science is called singular value decomposition. And also linear algebra does not have time to talk about this, so I will tell you this. So there are two decompositions that are all related. So I will first talk about so-called polar decomposition, and then I'll talk about singular value. Okay, so polar decomposition says that if I give you a linear matrix, so operator A, then there exists a unitary U and a positive operator, positive semi-definite are already defined as basically this record. So okay, so when I say J is positive semi-definite, meaning that so if you only for all X, X is greater than equal to 0, and J is Hermitian by default. And this is the same as if you are more familiar with linear algebra, that usually Professor writes this. So all the quadratic form. So all the basically is a quadratic form. So all the vector whether it's this or this greater equal to 0. These are positive semi-definite. I already say that. So this theorem tells you that you can write any linear operator A in terms of unitary times another positive semi-definite matrix. So you can always write A in terms of UJ. U is a unitary and J is PSD matrix. This is called left polar, and there's another way you can write it to the right hand side, basically. Some positive semi-definite times a unit. So you might feel, oh, this is weird, right? How people come up with this weird decomposition and unitary times a PSD. And actually, this is why this is called polar decomposition, right? Because in the polar coordinates, you take any complex number, you can write it as r times exponential I say that. Right? But this is polar decomposition. 高中反正大一的时候，你知道说可以把一个 complex 数一个复数写成是一个实数，一个半径乘上一个 face， 这个要学过。So if you look at this, you can see, oh, this is a positive number times a unitary, or basically the face, right? So that means that in matrices, you can naturally generalization of this fact into the so-called polar decomposition. So you just generalization. So you can write it as a unitary times something positive in terms of matrices, which is positive semi-definite. Okay, 所以你可以想这个 polar decomposition just a generalization of these polar coordinates, some positive radius times a face. So it's the same as some positive matrices times a unitary. 希望这样让你觉得比较自然。非常不自然。那so when A is invertible, U will be unique. Okay, so this is quickly. So the proof a little bit complicated, but that's it. So the proof basically is we want to write A in terms of unitary times of positive matrices, right? So the nice way to get J is to just take A dagger times A. So notice that A dagger times A is permission. Okay, and take A dagger times A submission because when you take it again, it becomes A dagger dagger. And so it's the same. So A dagger is submission. So that means that A dagger A is always you can always do using a spectral decomposition. And obviously that A dagger A is positive semi-definite. So we can take a square root. And yeah, this is I mean it's good for everyone knows this is positive semi-definite because you take any vector x, take a vector x, this can be written as AX in the by definition. Right, because the vector psi, the norm of this vector will just psi times that. So when you do this square, it becomes this. So this is always positive. Okay. So that means that A dagger times A, this matrices is positive semi-definite. So I can write A dagger A, I can write A dagger A in terms of some unitary times diagonal matrix, some diagonal matrices, and I take times the inverse. So I can take a square root by taking a square root on the diagonal, and then define this guy as a square root of A dagger A. So I define this matrix as J。再讲一次，就是说这个 A dagger A 这个矩阵是 PSD 矩阵，它原因是因为它乘上apply 任何 vector，那就是长度的。So A dagger A is a PSD matrix, and it's dimension. So I can define so square root of A dagger is well defined. Yeah, I define this as J. Okay, so I can so J is a positive semi-definite matrix, right? So I just provide. So you can use a spectral decomposition of J. So you can write J is the sum over I of lambda I. And I is orthogonal. So we just define psi I to be A times I. And the psi I, the norm of psi I will be lambda I squared. Hopefully this is obvious because so now you need to separate in two phases. So when you do a spectral decomposition on J, there are two possibilities. One is lambda I is non-zero or lambda I is zero. So when lambda I is non-zero, then you just define this EI to be this psi I divide the lambda I, right? Because lambda I is non-zero, so I can do division. And then EI to EJ will be in the product of I and AJ divided by lambda I lambda J. But notice that spectral decomposition tells me that this I is orthogonal. So when I differ from J, these are zero. Okay, because this J is eigenvector of J. J is squared. So they share the same eigenvector. So this EI and J also. Okay, so if for lambda I is non-zero, I get a set of orthonormal vectors. But maybe there are not enough to span the whole vector space, right? But I have this Greenstreet process. I can generate the rest of vectors such that they span the whole vector. Anyways, 我一开始把所有lambda I 不是零的那些向量全部抓出来，我发现它们是正交的，但是它们生成不一定可以生成整个空间，对，所以我把剩下来的那些，我就从剩下的向量随便抓一大堆，然后让它们生成整个空间，然后使得大家都正交。啊，这个是可以用到，因为有一个 Greenstreet process。有没有讲 ？Okay, now I define unitary operator for U divided by EI and I with this EI over now. So the easy exercise to check the equals unit. Let's do the computation. By the way, this program not complicated. You just do the simplification. Okay, so we just define is Alright. Oh, by the way, so sometimes I will write the initial and the end, but yeah, sometimes people are lazy. So do this way. So first thing, you can check that you can so it's easier enough for you to check use unit. The reason is that you just mapping one I also know vector to another. So you basically change your basis. So use unit. So I want to connect that. I want to connect basically connect A equals to U die on all the bases. So for lambda A is not 0, let me just apply this UJ acting on I. UJ I, right? So the J is lambda I apply on I, right? So when you apply on I, let me address this. Okay. Wait, we know this, right? So what's J apply on I? We get on the I, right? Right. Is that right? Okay, so now I can apply U here. So I apply U here. Okay, so what's U acting on I? It's basically EI. Okay, so it's maybe a little bit fast, but it's there is U acting on I. So now I need to change it to J for the calculations. Okay, so J. Okay, so I get sum over J, EJ, JI. But IJ is also normal, right? So the remaining will, so this is the alpha IJ. So the remaining, so sum over J is the same as the just leave I. That's okay. 没有，所以这个 U apply on I 就是又变为 EI 了。So U apply on I 就是 EI 了。So it's basically lambda I. Okay. And lambda EI by definition is this psi I, right? Yes. Lambda times EI is psi I, right? Psi I. Okay. And by the psi is defined as A times I. So this is A times. Okay, so this means that apply on I, UJ apply on I is the same as A apply on I. Okay. Okay, so this is for the lambda I not 0 case. So when lambda I is 0, it's easy to lambda is 0 is trivial because when lambda I is 0, then UJ I is 0 and the same as for A apply on. So that means that A equals to UJ on all the bases, on all the orthonormal, on all the bases. So that means that A equals to U times J. 就是 A apply A 等于 A 跟 UJ 在这个 orthonormal basis 上的作用完全是一样的，所以 in terms of matrices， 你把它 expand 它就行。这证明可以回去想一下，也不是很困难。Okay, so the uniqueness of JU. So notice that if I write A in terms of UJ, that A dagger will be J times U dagger because J is permission. So A dagger A will be just U dagger UJ, but U is unique, so J squared. So that means J is the square root of A dagger. It's unique. So that means that if I write A in terms of UJ, then J is always uniquely defined. But if A is invertible and J is known, then U will be uniquely defined. Because I can write U in terms of H and inverse. If J is invertible. But J is invertible if only A is invertible. It's obvious. So okay, so obvious that if A is invertible, if and only if the determinant of A is non-zero. Right, it is the linear algebra. Linear algebra, of course, tell you that the matrix is invertible if only if its determinant is non-zero. And obviously that determinant of A dagger A will be just determinant of A absolute value square. It's also linear algebra. 有学过，对，现 determinant of A dagger A 跟 determinant 的绝对是一样。So obvious that if A is invertible, then determinant of A is non-zero. Then determinant of A dagger A is non-zero. So that means that A dagger A is invertible. So if A dagger A is invertible, that means that J is invertible. If J is invertible, then U is uniquely defined because I write A in terms of UJ, but if J is invertible, then U is AJ inverse. And U is uniquely defined. 这只是说，如果这个只是说，这个就是回到那个刚刚 ，so this you can go back to your polar coordinate, right? So this just tells you that if this number is non-zero, then all these are uniquely determined. 回到这个这个大学大一的时候，这个 polar coordinate 这个极坐标嘛，极坐标就是你只要不是零的话，这个 r 跟 theta 是固定，就是你画在平面上它就固定。So these are like yeah. The right polar decomposition is exactly the same. Just repeat the left to the right. Okay. Alright, so finally is the singular value decomposition. This is called the SB. So this is probably the most important one because any matrices you can compute SVD. Now you just in Python you just write one line. Just write SVD and there's they will output the result. So if you give any square matrix A, there exists a true unitary. One is U and B, the diagonal matrices. But with non-negative entry, such as A can be written as U, D. So this looks very like similar to the diagonal spectral decomposition. But notice that their matrices are different. U and B are different, can be different unitary, and the D must be non-negative. 这叫做奇异值分岐中文。So the element of D is called singular value of A. So this theorem is interesting because it's somehow a slightly generalization of diagonal matrices. You just allow different matrices in terms of if you allow different decomposition, the different unitary to the right, then you can somehow choose this D to be always non-negative. Alright, so a proof will be simple, right? The proof is that I already know matrix A is I can use a left polar, right? So I can write A in terms of S times J, where S is unitary and J is positive by positive semi-definite by previous results. That is the polar decomposition. Unitary times the positive matrix. And this positive matrix is Hermitian, right? So I can use a spectral decomposition to apply on J. Such that I can write J in terms of T, D, T. Okay. Such T is unitary and D is diagonal. And then now J is always non-negative because J is positive. So I just use polar decomposition and I use spectral decomposition on that J. Right? So A can be written as Sj. This is polar decomposition. And I write J in terms of spectral decomposition. So it's T, D, T there. So I combine with S and T. And D, T there. And notice that S is unitary and T is unitary, so they are per dial unitary. So I can write a matrix. So I define S to be U, and T to be V. 没有问题吧？证明就是用两次，就是你先把 A 写成是 polar 的 decomposition， 就是一个 unitary 乘上一个发生那个正定矩阵，然后就把这个正定矩阵呢用 spectral decomposition 爆开成 unitary 乘上对角矩阵乘上 U， 然后把两个 unitary 拼在一起。就这么完，就变成 unitary 乘上一个对角矩阵乘上另外一个 unitary， 有没有简单 ？So this is a proof is very simple. You just apply the. By the way, so in your linear algebra textbook, usually the textbook will first prove the singular decomposition and use singular decomposition to prove the polar decomposition. Okay, so the easy exercise for you is to assume singular value is correct, and then you can try to prove the polar decomposition. But actually, they are the same. Okay. 这个就是说，我的这个证明方式是从 polar decomposition 证明 SVD。那你可以回去试试看，你可以假设 SVD 是对的，然后证明 polar。这个应该也是，这反问他们是一样的。
就是他们可以互相证明。OK，
So why people care about SVD? The first is that you can apply on all the way. Yeah. But validation is not. For example, simple exercise is to check this guy is not validated. Uh, okay, so this is an easy exercise. Okay. And you might know the so-called analytic computation of Jordan form, but it is so complicated. That's still the use.
Okay, so maybe you know some machine learning, right? So first, the simplest unsupervised learning
Methods in machine learning is called principal component analysis. So yeah, this is not related to the course, but you just tell me that if you know machine learning, there's an algorithm called PCA. And what this algorithm does is you just take a data matrix X and you just do the single variable decomposition. So single variable decomposition is exactly the same as PCA. So if you heard about PCA is like so famous, but PCA is just single variable decomposition. It's exactly the same thing.
就是 machine learning 里面有很多算法，其实都抄 BCA，因为都抄这个 single value composition。
The reason is that this single variable decomposition can make you to reduce. Let's say you want to reduce your data or reduce the If you do the so-called dimensional reduction, you give me a matrix, right? I can do a single variable decomposition and then take maybe the first 100 largest single value to be my to reconstruct the matrix, and this will capture most of the features. 这个就是说，你给我一个够大的矩阵，你给我矩阵很大，对，我没有办法把矩阵，我要把这两个矩存下来，我要留住它最重要的资讯。那我就是把它最大的几个 single value 抓出来就好，那我就可以压缩一个矩阵。
对，这是一个常见的做法。
Okay. And if you know some like condensed matter theory, there's a computational method in condensed matter theory called tensor network. 这个 tensor network 就是这个有点复杂。我 tensor network 的算法里面的其中有一块大部分也是用到这个 SVT。
你可以看算法，基本上大家都是用 SVT。
Okay, so yeah, so we finished linear. So all concept basically is breaking notation are fundamental linear. So basically, so all these vectors, I mean, until up to now, they are all can be irrelevant to the quantum computer, but it can be applied on machine learning or other kinds of things. So basically, I compress the semester of linear algebra in 1.5 sections. So just make it to reduce your linear algebra textbook, and then yeah. And so we have compressed like 1.5 vector. So I will try to compress 1.5. I will try to compress the whole quantum mechanics and physics into 1.5 vectors. And then so that you can cover the minimum essential to understand the quantum computation. No worries, here are these are. Basically, you don't need to know all of them, but I just tell you that maybe if you forget about some detail, that you can go back.
那我们就花了大概90分钟的时间，就是反正没那么多，就90分钟的时间，没那么多，就1.5个小时1.5个 lecture 的时间，把线性代数一个学期所有的概念都走过一次。So yeah. By the way,
so these are the versions. By the way, you can just download this PDF. Yeah, I will say yeah, you can just download the PDF if you forget about. Yeah.
Oh, so except for this Jordan phone, yeah. If you are interested in Jordan phone, then yeah, you can try to learn it. Okay, so
if you see the textbook, if you go see the textbook is Nielsen in front. All of it is just a small fraction of chapter 2. Okay, so basically 2.1, the second 2.1. So 2.2 is basically the so-called postulate quantum mechanics. So hopefully the rest of the 40 minutes, I will tell you that actually you don't need to learn all the quantum physics and quantum mechanics if you just want to understand some basic principle, or maybe you want to do research in the quantum computing, you don't need to know all the detail of this quantum mechanics. And hopefully I will convince you.
那我就想说，这个如果你要做量子计算的话，其实你就是看你要做什么方向，但是你不需要理解整个量子物理很多细节。那原因是因为原因等一下就知道了。那我先讲一下，我先看我要怎么 OK。我的希望可以说服你，就是你不需要懂整个量子计算，你不需要懂整个quantum mechanics。
Okay, so I will introduce the essential quantum mechanics for the quantum computing. So there are some code that quantum mechanics is easy if you take physics on. So the key idea is that if you want to compute, let's say, energy level of hydrogen or electron, you have to do a statement. Or you want to do some interaction, magnetic interaction. Sometimes these are not the essential quantum mechanics. These are some you just require more advanced mathematics to then you compute all this. So these are not the essential of the quantum mechanics itself. So for quantum computation, you don't need to know all.
Okay. So the reason is that I propose the following classification.
So this is out so I just read. So I just characterize this quantum mechanics or quantum information into two areas. One is so-called continuous quantum information, or so-called continuous variable quantum. These are like so-called photons or bosons, or even there is simple quantum field theory. It involves the infinite dimensional Hilbert space. And so these continuous variable quantum systems, they are related to more related to so-called mathematical physics, and rely on some analytic tool, like partial differential equation, or the complexness, and maybe sometimes you need some more abstract, the algebra, the evolution, mathematical. And another area is called the discrete quantum mechanics. 就是一个是也学一个是占。那this is more like relevant to electron engineering, or computer science. So it involves the discrete mathematics. And to understand most of the idea, you just need to learn the basic algebra and probability theory. 也就是说，上面的是延续型的量子力学，它需要比较多的基础。如果你只要了解 quantum computing 的一些东西，或者你做某一块领域的话，其实你只要懂enough 的 linear algebra and the probability theory 就 OK， 不用全。You don't need all the whole PD or unless you're conducting some like theoretical research. Okay. It's yeah, so I will spend a few slides on the why this part of quantum mechanics is hard compared to the okay. Actually, they are all difficult, but they are not difficult as same. They are not difficult as different aspects. Okay, so one reason why quantum mechanics to learn that in physics department or other like different engineering department, the first time you learn quantum mechanics, you feel like they are difficult because actually you are fighting with so-called infinite Hilbert space. It's different from this linear. So I will tell you, I will try to give you some example and then you forget it.
Oh, by the way, these are not in the textbook. These are just my opinion.
So yeah, these are just some physics if you have never heard about it, fine. So in physics, maybe you heard about this so-called simple harmonic oscillator. 对，叫做这个有听过？ So these are simple. They're so-called quantum harmonic oscillator. So you just write so-called Hamiltonian in terms of the fixed rate and Einstein. So these are harmonic oscillator. This changing this p and x in terms of so-called operating function. Now we can define so-called negative operator. A and A. These are all quantum physics. Okay. So you just write A and negative in terms of. And you know that in quantum mechanics, right? The first axiom, or at least the textbook, what textbook tell you is that you just replace x and xp in terms of say it or like so if you use this commutator of this x and p, then you can easily check. Then you can easily check this correlation and deviation of the satisfy one formula of this bakery equals commutator. 这个要读，就是
就这个经过这个量子力学，老师有跟你讲过，就是这个好像应该是大三的那个课程，应该有讲过这个叫做简谐正子。然后 once you do the operation and ideation, then you can prove that they have this formula A and A negative commutator equals. Okay, so my question for you is that I claim that this commutator relation implies the Hilbert dimension is big. 有没有知道为什么？So I want to say is that you can forget about everything. But if someone writes a formula telling you that A, there's an operator called A, there's another, and they say bigger A, bigger the commutator equals 1, then this space must be, then this operator must exist in infinite dimensional space. 老早在说什么？就是说你在学量子力学的时候，如果老师讲到这边，对不对？你看到这式子，你会说，哎，没什么嘛，就是这个推出来的。可是你如果一直看，你会觉得很奇怪，就是其实这个式子代表你这个空间绝对不可能是有限的。Okay, so the proof is simple. Remember that we proved. Remember that previous I just proved this, right? This trace is secret, right? So, but this tells you what? This tells me that this term, right? Sure. But this tells me that commutator of AB must be 0. Trace. 对吧 ？trace of AB 应该0 commutator of AB 但这个 trace 一定是0，因为这就是 trace AB 等于 trace BA 嘛，就废话。那你现在 so if you believe this is true, right? So we prove let's say you replace A and A dagger just using that, right? So this will tell you that this is 0. Right?
But that implies like that assumes as well that they are diagonal bases.
No. I mean, this is true for this is true for arbitrary matrices for any finite dimension.
Oh, that's right. Yeah.
Yeah. So
we haven't yet proven, of course.
Yeah. So that means that if A and A dagger are infinite dimensional matrices, how can this guy be identity? If this guy is identity, then how can this trace identity is 0? 就是说你如果说 A 跟 A 那个是1好，那是 identity， 那它怎么可能 take trace 是 0？ 你一个 identity you take identity matrix, the trace can never be 0. So that means that A and A dagger, this operator algebra can never sit into any finite dimensional vector space. If there is a way that you can write A in terms of finite dimensional A dagger in terms of finite dimensional, then you must get something contradiction. So that means that this kind of algebra, they are naturally sit into an infinite dimensional Hilbert space. 我会中文再讲一次，就是说，你如果相信，你如果被我刚刚说服说 trace AB 等于 trace BA，这不相信，就你可以证明。那你自动就会你 price 说 commutator of 任何2个矩阵在 K 区都是，可是这就违反了 A 跟 A 的本身 commutator 是1嘛？因为是1怎么可能？你 trace identity 不可能是0，对不对？所以就表示说这个式子它本身这个
So we use that it is finite dimensional in the first set.
Yeah, actually, yeah. So this is why in your proof in we use summation, right? But we exchange the summation order. So we need this. So this is true for finite dimension. So it's basically a proof by contradiction. Suppose these are finite dimension, then I get contradiction. 所以就说你这个量子力学里面，你这个量子力学它把方量之类的本身是无穷微，它没有办法被限制在有限的世界当中。Yeah, so this is our like all common stuff that we're talking about this. Okay. So this relation, yeah, this is. So that means that this is why so this just tells me that the quantum harmonic oscillator is infinite dimension. And yeah. And these are another example that tell you that why is infinite dimensional objects here. So maybe in sorry. So previously we talked about this quantum harmonic oscillator, right? So I want to tell you that there is some exotic object in this kind of vector space. For example, there exists a state called coherent state. So notice that this vector space is infinite dimensional. So all the elements can be written as a linear combination of energy state A. So this A is a harmonic oscillator, right? Harmonic oscillator, the harmonic is n plus f transformation power。这个量子力学有学过的，就是量子力，就是harmonic oscillator 的能量是 n 加2/1乘以双。N 就是 the number of 就是 energy level 从0到无限大都有。So all the states should be written as linear combination with these so-called full bases，就是从0，对不对？ And A has a property that by n will decrease n. So this is why A is called NP operator and A is a conjugation operator, because one will increase the n and the one will decrease n. 这个应该是有，这个应该是大三的时候有，third year quantum physics if you heard of it. Okay, so I will tell you that they're in. So okay, so let me just write that. So there exists. So this vector space are infinite dimension. And every element and each state inside this vector should be written as a n. Well, n can be from 0 to infinity. It's different from 5 dimension. It's not 0, 0 tends to 0 or whatever. It's from this able by integer from 0 to infinity. And this an need to be normalized. Right? So these are infinite vector space. 这个是harmonic oscillator 的向量state 存在的空间，有无限多的能量，对不对？每个能量可以取一个系数加起来，啊，不要爆掉就行。要是再来。Okay, so there are exotic objects inside this vector space. So I just want to tell you why quantum mechanics is hard. Right? So for continuous version is hard. So this is a weird object called the coherent state alpha. So this alpha is any complex. So it gives me any complex number. I can create a state looks like this. For Hn with amplitude alpha to n divided by square root n factorial n times this. This is called the coherent state alpha. Is it? Okay, so let me write down. So alpha is defined to be that. 如果没有听过，可以听听看，就是可能会觉得奇。Right, so these are well defined. 对吧？你每个 n 我都多一个 ，so easy to check that there are all sums. There are probably there satisfy this normalization condition. Okay, I can check it for you. So a n will be just be this, right? So if I take absolute value, I get this. Next, if I sum over n. Then I get this n from 0 to infinity, alpha to n factorial. Then notice that this is exponential alpha 3. Okay, so you can check that these normalization, these are indeed the correct normalization. 因为你可以 compute， 我给你个 alpha, right? Look at this, then you can compute norm, right? You just take the number and do the absolute value square. So you get an squared to be this square and alpha to n divided by n factorial. And then you will sum over n from 0 to infinity, then this is constant, and this is n from 0 to infinity, so alpha absolute to n divided by factorial. 那这个东西刚好是太阳展开了 exponential alpha 平方，把两个刚好消掉。Okay, so you might say, oh, but for what else, right? This is just some weird state, which is can be is some weird state, right? But one interesting fact is that this alpha is indeed the eigenstate of operator A. So you can take A and apply on alpha, and then this will give you alpha times alpha. And the reason is that I can check. Let me just do it. So this is alpha, right? If you times A times alpha, and from 0 to infinity, and alpha n square n factorial. So notice that when alpha applied to n, remember the previous slides, right? Sorry, when a applied to n, we get square root of n times the minus. So you just get square root of n minus 1. And the square root of n and square root of n cancel, right? So you get square root of n minus 1 factorial. And you can just take out one alpha. So you got n minus 1 times the whole alpha. Now you change 0 to infinity to 1 to infinity. So this guy becomes a set alpha n minus 1, n minus 1 factorial, n minus 1. So this is also still. So that means that a times alpha is the same as alpha times alpha. So alpha is eigenstate for a, but for arbitrary complex number alpha. But this is weird, right? Why? Because this vector space has a countable basis, but it has but A operator has uncountable eigenvector called alpha. 大家有听得懂吗？就是说这个 state alpha 呢，它是是所有，你随便给一个 alpha， 我都可以造一个 state， 它是 A 的 eigenbase， 它是 eigenvector。可是这个 A 可是这个 alpha 是 uncountable。uncountable 就是说它数量比整数还要多。可是它存在于这个世界，可是它竟然可以把，它竟然是所有的，就是它这个 A 竟然有 uncountable 那么多的 eigenstate。So that means that A has more eigenstates as this dimension. If you naively think about it, because this dimension is countable, right? It has a natural number, but A has more uncountable eigenstate. Because you take any complex number, I can create such eigenstate. And also that you can check, you can learn a simple exercise for you to check that. How about A dagger? How about A dagger? 就是我说 A 有无限多个 eigenstate 嘛，我已经找出来了，我就丢在那边。我是说，如果 A dagger 呢 ？A dagger 有没有无限多 eigenstate？ Okay, so easy non-trivial exercise for you is to check there's no eigenstate for A dagger. A dagger 没有任何 eigenstate。你可以 you can check. You can write this state and then apply A dagger on it. And then try to see what's the condition for AN such that this state to be eigenstate of A dagger. But there's no eigenstate for A dagger. So that means that in like infinite dimensional vector space, right? Sometimes that in right operator there may not be eigenstate. Sometimes you get infinite, you get a lot, right? Sometimes you don't. So that means that there are exotic things happen. So this is why even this simple harmonic oscillator is very, very deep mathematical structure. So this is why like you start with simple harmonic oscillator, but you get some system which is you get very exotic object inside it. Oh, by the way, previously something easy from the if you're serious about like from the optics, that people would say previously is actually easy. So there are more exotic objects inside this. There are more exotic objects inside this state. Inside this vector space. Okay, so this is why your standard linear algebra tools are sometimes insufficient for it describe all of these exotic objects. So you need some other mathematics. By the way, these are actually this space is has a name called single argument space. You can go to Wiki and see the difference. So I just want to tell you that this is why infinite dimensional vector space is interesting and hard. Okay, so yeah, so we forget about it and go back to finite dimension. Okay, so I will try to describe some like axiom of quantum mechanics, and there are 3 of them, but maybe we just talk about one and 2. Okay, in this Nielsen or at least in this quantum computing framework that one can view quantum mechanics just a mathematical framework for developing like physical theory. So I will just tell you the axiom. So the axiom is like you don't need to ask why, but just the axiom. Okay, so you just try to apply that. This is the same as I mean I don't know, but this is the same as when you come to the physics, you go to some physics course and you learn some differential equation like Maxwell equation or Schrodinger equation, and like somehow like all the course just tell you that if you believe this equation is true and you do a lot of homework and you do some computation, then you arrive something. So this is somehow like very similar to mathematics that I tell you something is true and you need to believe X axiom and you see how this axiom goes。就说这个不知道大家在学校念书，就是有没有感觉，就是说这课有时候就是，当然老师会 inspire 你说某一些方程式是对的，但是你从你的整堂课就变成是说，你假设这个方程式是对的，然后你去看它能告诉你什么结论。那比较常见就电磁学嘛，电磁学就是你从 Maxwell equation 出发，然后你看你能得到多少东西，你一整年都在做这个事情。那量子力学是 you start with professor tell you that the Schrodinger equation is true, and you start to solve different potential and see what's the results. So 这个基本上所有课都是这样，就是有一些东西是对的，就是我们从某一些假设出发，然后看这些假设能够导引到什么样的结果。这个其实这也是有历史啊，我算这下次再讲故事。So postulate one. So there are three postulates you can do it actually. So the first postulate is true. So you have to say that let's say you take isolated. So I will define what isolated is. But let's say you take some isolated physical system, and so the description of that system can be represented as or actually all the states, all the possible description of that system can be related into one universe space, or basically universe space with finite dimensions. At least in this course. So basically, simply speaking, is that this system is completely described by the same vector and a unit vector in this. That's all. Okay. So this theory just have that if I want to describe a system, then I use a state. So a state is a state vector with basically a vector, a unit vector in a finite dimensional universe. Basically, some finite number of complex time. 这个第一个 axiom 就是很像是废话，就是说我描述一个状态呢，我要描述一个量子态，我就会用一个complex Hilbert space 当中的一个向量，等于说我用一个复数向量去描述一个状态。好了，没了，就这样。Okay, so very simple. Theorem. So this postulate one looks like trivial. This is the same as linear algebra is a correct language. So this is just the first axiom. Okay, so the simplest example of fundamental or basically what we call at least in this course, so-called qubit. Qubit is a two-dimensional space. So I use 0 and 1. Oh, sorry. So 0 and 1, 0 and 1 is 0, 1. So 1 0 is the basis, and by definition, the arbitrary qubit state. And so so you take a qubit, right? By the previous axiom, telling that all this description of that qubit system must be written as A0 plus B1 with unit vector, right? So after the value A squared square. This is also why this one. So I would like as the qubits. I like that's okay. A qubit can be superposition of B1. Superposition 就是这两加起来。this addition is called superposition. Okay. So this is just trivial. It's two-dimensional. It's a two-dimensional vector A and B. Okay. And yeah, so basically any general quantum states, basically some linear combination of some basic state. This is called superposition, and this alpha I is called amplitude of the state. Yeah, this is where. Okay, so for example, maybe I will write 1 squared 0 minus. Okay, so this is superposition with n equal to 1/2 and minus 1/2. So these are simple. Okay, so somehow this is the second postulate. So postulate, the second postulate tell you that if you want to start with a state and then transform to another state, right? This is what we need to do. It's like dynamic. Somehow, like if you come into like physics course that most of the problem tell you that most of the course tell you that how to solve so-called dynamics, right? Start with some initial condition and you evolve. But most of the test systems are continuous, so this is why you use a partial differential equation, right? But now we are in the finite dimensional case, so we don't need to use a partial differential equation. We only need to use somehow like linear algebra. So the axiom basically tell you that you only allow transformation from a state to another state, basically the unit version. Right, so this is the axiom. The axiom to tell you that if I want to start from one state and transform to another state, I need to apply a unitary matrix or the unitary operator. So this is the evolution. So evolution depends on only initial and final operation. Problem K is guaranteed that it exists of U, but nice. So this is the second axiom. Basically, the second axiom tells you that if you want to build a quantum computer, you only allowed transformation on unitary. These are all true. So the unitary operation on 2-bit, for example, that's only x. Okay, so now we can use this notation. So I know 0 is. So I know 0 is this right. So these are now I can really use this. I can really use this branching notation. Right. So remember that x is 0, 1, 1, 0, and then 0 is. So I will use this. So I will write it maybe a few times, but yeah, but the later course I will not write this 1, 0, 0. Okay, so obviously when x equals to 1, 0, they apply to basically 0, 1. And when x equals to 0, 1, when x on 0, 1, they become 1, 0. So x just change the 0 vector to 1 vector. So x apply on 0 become 1. So and when x apply on 1, it becomes 0. So this is somehow different notation for the Pauli matrices, but more compressed one. So this is why x is also called a bit flip, because it flip a bit. Right? Let's say this is 0, flip 1, 1, 0. So this is a good thing for you to remember what's the property of x. You just remember x is a bit flip. When you apply on 0, it becomes 1. When you apply on 1, it becomes 0. Okay. So it is easy to remember. And another way for you to remember is how z is so-called phase split. So phase split meaning that when you apply to 0, then it's same as they just give you 1. When you apply on 1, then get an additional minus. This is called phase split. Okay, so yeah, so now if you remember these two, then you can reconstruct Pauli matrices easily, and this is a different way to remember Pauli matrices. And you might ask, how about y? So the one way to remember is y by definition is just I x times z. You can check it. So y is defined to be I x z. I can do it for you. Okay, it's very easy. So the standard y is just this, like 0, 0, minus. Alright. Okay. So if you apply y on 0, right? So let's say I apply on let's say 1, 0, right? Then you get minus I, right? Okay, so you get minus I1. And then when you apply y on 1, you get I0. Right? So this is the usual matrix representation of y. From here, then you get this, right? But I tell you that y can also be written as I times xc. So now we can check whether ixc is the same as y apply on these two. If they are the same, then I know that y can be written as ix. So I z apply on 0. So notice that 0 okay, so you need to remember phase flip and phase flip. So z apply on 0 is the same as z 0 sorry, 1 times 0, right? So that I x right. Oh, maybe I missed my but that's really yes. Okay, so you get this, so this is phase flip. One. Oh, maybe so maybe the minus I got here. So let's say here. Minus I, minus. Okay. Let's say I could I x z apply on 1. Now I get additional minus 1, right? So I get so if you apply minus I x c apply on 0, then you get minus I 1. And then apply minus I x c apply on 1, then you get I 0. That should be the same as his. Yeah. Okay. So that means it's minus I x.
Where do you do the calculation first? Should you swap the minus there?
It should be minus here.
Minus there.
Yes. Oh, sorry. Yeah, this is correct. It's right. So that means that yeah, so the original one is correct. Yes. Yeah. So basically, so you just need to remember x is a big flip, and z is a phase flip, and you can remember y. So this is somehow like a different notation, but exactly the same thing. Oh, now there are another one which is still the protocol is called Hadamard gate. This is most important. So this Hadamard gate will apply on 0 will be superposition of 0 and plus 1 divided by square root 2, and h apply on this 1 will be 0 minus 1 divided by square root 2. So if you're written as a matrix form, your h will be 1 over square root 2, 1 1 minus 1. So this Hadamard matrix is sequence. So this matrix is just the definition is simple. When you apply on 0, just linear superposition 0 1. When you apply on 1, there's addition to minus. So this is called a Hadamard gate. Okay, so why we need this Hadamard gate? The definition is there, right? But one important property is these Hadamard gates somehow like change x and z. It's not so obvious. So the first thing is to check that. So I know that 0 and 1, right? 0 and 1 are eigenvector of z. Because when z apply on 0, then becomes 0. When z apply on 1, you get additional minus 1. But what's the eigenvector for x? Right? Remember, x is a big flip, right? So indeed, this 0 plus 1 divided by square root 2 and 0 minus 1 divided by square root 2 are eigenvector for x. And for example, if you apply on x, apply on this 0 and 1 divided by square root 2, notice x is a big flip. So it will flip 0 and 1, right? So we get 1, 1. But it's the same. Because flip 1, flip 0 and flip 1. So 0 plus 1 divided by square root 2 is the plus 1 eigenvector for x. Because x will be flip 0 and flip 1. So it's 1 and 2. Right? And also x apply on 0 minus 1 divided by square root 2. Right. So b flip is 1, b flip 0 divided by square root 2, which is minus 1, 0 minus 1 divided by square root 2. Right? So that means that 0 plus 1 divided by square root 2, 0 minus 1 squared divided by square root 2 are eigenstates or eigenvector for x. So these are eigenvector for x, these are eigenvector for x. So this h somehow like transform the eigenvector for z in terms of eigenvector of x. So indeed, this h will transform the x and z. So yeah, so let me just write down the algebraic results. Definition is important. So the easy exercise is to check if you apply h on x, you get not so obvious. So to prove this, the easy way is to use a notation that say this is common notation. Sometimes this called plus state. Sometimes this is called minus state. 这记号也零加一几个根号就叫正，然后就 So the property for this is x apply on plus, it will be positive. When x apply on minus, it will be minus minus one. So if I notice this, then I can prove this. Right? So the proof is very simple. Let's say I apply this to 0. Then I get plus state. By definition, h apply on 0 is a plus state. 是 0加1除以根号。So this is hx plus. But plus state is the eigenvector for x. 刚刚就是这里。h apply on plus 就是 plus。所以就是 h apply on plus state。那 h apply on plus state。不要忘，这个 h 是 unit term。So easy to sorry. One fact is that h squared is identity. You can one can check. 那我们可以反正这个 h apply on plus states 我们可以试试看它其实是 C. So let me just write down the final. So the remains to show that h apply on plus state 0. Right. But yeah, there's a various way to do it. But if you can brute force compute it. If you notice this is true, then by definition you already know plus is h apply on 0. So h apply on plus will be h squared by h squared is 1. So h apply on plus will give you 0. So if you compute h apply on 0, you get hx plus. You get h plus is 0. And the same as if you compute hx minus, sorry, the 1 state. So h apply on 1 will get you minus there. But minus state is minus 1 eigen corresponding to the eigenvalue minus 1. So you get h apply on minus 1. But h apply on minus 1 is 1. So these are just some algebra, but what I want to say is that the property why people don't care about is Hadamard, because Hadamard will exchange x and y. So the only thing you must remember is that these are 0 and 1 are eigenstate for x, and these are 0 plus or minus 1 are eigenstate for x. So these are for z, these are for x, so h maps the eigenstate for z to x. So this is why there's a transformation there. You can prove this by using the matrix form. You just write h into the matrices, x into the matrices, and do the matrix computation, or you can just apply it on the base vector. Okay. So the next is that so previous just you allowed to do unit, right? But so in physics, right, sometimes that there's a formula function in the equation. So it tells you that the states involved 这个意思。这样看过，这个知道的。就这个是对应的方式嘛，比如说有一个很多年apply state， 那就是变成这个很多年会决定这个 state 的So you might feel, oh, maybe this is different from postulate 2, right? But indeed, this is the same because what? Because you can show the state evolve. Basically, it's the same as uniform.
Okay, so this Schrodinger equation tells you that this like this. If you write as differential, then it become like exponential minus I t divided by if h is time dependent, right? And this is unitary. Okay, so actually, I just want to say that the previous axiom tells you that the only allowed operator is unitary, but this is indeed the same as this Schrodinger equation. Because I give you a Schrodinger equation that the evolution is basically some exponential or minus I Hermitian matrix divided by t times h apply on side zero. And obvious that this is unitary. This is good. The reason is that h is Hermitian, so they have eigenvalue also this already. Okay, I think this is for today. So next time we will talk about a measure. I think this is we just finished the postulate 1 and 2, and postulate 3 is complicated, so I need one hour to explain. So that's it.